I'm very pleased to be here tonight to share with you a very big idea University of Tennessee has pursued to establish a National Manufacturing Institute in composite materials. We had three goals to start with: to reduce the carbon fiber composite cost, reduce the energy it takes to make it, and then substantially improve the recyclability. As you can see from this goals that we promised to Department of Energy 5 years back, we were going to cut down the cost of making these by a quarter, reduce the energy by half, and improve the recyclability by 80%. And this is a slightly better idea than a tiny trash we're going through right now. So the IACME has several aspects of doing business here, but University of Tennessee and Oak Ridge National Labs jointly lead the materials and manufacturing methods, and we work very closely with Purdue University in developing modeling and all the other partners, as we will learn today. So within materials and processing, we work with Kentucky to make polymer fibers. We carbonize them at Oak Ridge facility, and we make composites, and then we make them integrated into full-scale components like wind turbine blades. So this is an example of a very small wind turbine blade. It's 9 meters or about 30 feet long. And so you make it in two halves. It's an airfoil design. And then in between, you have a load-carrying member, which is like an I-beam. And all of these have to be very strong and very lightweight. For General Electric right now, they're going to make 100-meter-long wind blades. So carbon fiber is going to be like an essential material of choice for them. It comes in a filament form. It's about 7 microns in diameter, and that's about 1/4 of a human hair. And then we make various material formats from which we make composites, as it's shown in here. So just to give you a sense of how strong it is on the y-axis and how stiff it is on the x-axis, we beat steel by miles, any type of carbon composites, and it's 1/6 of the weight of the steel. So you know the future is going to be made out of carbon fiber-based material systems. So this is an example video for you to see how we make high-pressure tanks. So essentially, we take a liner that's made of aluminum and overwrap this carbon fiber, and that increases its ability to carry very, very high-pressure gases and things like that. And we have various types of fibers to target the design requirements. So you can see as an example here, this is the products that are manufactured by a company called Teijin, which is very close to where we live. And you have compressed natural gas storage tanks, all the way to our brothers in arms every day with firefighters carrying a lightweight oxygen tanks. And even their coats are made out of carbon fiber, partially oxidized. This is an example project that UT is leading to give you a flair of what kind of projects we work with. In addition to making these tanks lightweight, strong, lower cost, we also are making them smart. So we integrate fiber optic sensors so they can monitor their own health, and I'm sure they will perform better than the Max jet that you're all concerned about. So this is example analysis first we do with finite element modeling, and then these are very difficult systems to model because you have fibers, you have resin, you have interfaces, you have metals, but then we go through a lot of validation, and then eventually what we want is products that help you. This is an example of a Chevy Stingray, and the key I want you to get from here is weight. Weight matters everything in automotives. Lighter weight, the more gas money you will save. So the automotives can get enough of the carbon fiber as we move forward. BMW is one of the first smart companies to realize this. They invested 2 billion euros and transformed their metals manufacturing facility to use carbon fiber composites. So i3 and i8 have really put them about 10 years ahead of all the US auto manufacturing facilities. Now they're trying to catch up working with us. So the real key is money. It's always about money. And composites, the 60% of the cost is carbon fiber. So we early on decided that if we're going to make a big dent, we got to take care of cost of carbon fiber. So that led to us making a strategic move to identify how can we move from aerospace type applications to commodity applications like automotives and wind turbine blades. The ones that I've highlighted in the red are the key, the cost, how quickly we can produce them, and can we scale them up to the scales we really needed. So just to give you a sense, right now we produce about 10,000 tons of carbon fiber in the US. If Ford works closely with us on a number of projects, if they just simply use 4 kg of this material in every car, then we use up all of the material we produce today. So we expect 100-fold increase. So if you got some free money, think of the investments. And as far as the strategy for our institute is concerned, we are revolutionizing the feedstock material. We decided that we don't need aerospace properties for a lot of the other applications we discussed, so we kind of taper back on the requirements on the properties and then economies of the scale. This is an example of how we're reducing the carbon fiber costs. So this is a polyacrylonitrile polymer fiber that goes into your white socks that you all like to wear. So now we have a technology that can convert that fiber into carbon fiber. So we took away a lot of cost of separately making the fiber to make the carbon fiber. Then my group members have a lot of toys. On the left is a high-resolution X-ray computed tomography. So we make the materials, we study the process property relationships, and then provide a window of how these material systems can evolve for various application needs. I want to leave with this desire. I know those of the bikers in this audience know we all like to have a carbon fiber bike, but you can't afford it most of the time. Now you can afford it with our low-cost carbon fiber, but in addition to that, we're making it smart. This is actually Greg LeMond's bike that we got access to by Mr. LeMond. We instrumented it, and now we have a smart fiber optic sensor. So I won't tell you the weight of the person who is on it, but we exactly know where the stresses and strains are concentrated, and we put carbon only in those locations, further reducing the cost. So this is the future, and I hope you will be looking for the next phase of the goal, which is going to be black carbon. Thank you.